Yesterday we talked a little bit about when we took the composite and it equals x, that is considered an inverse function. So we're going to see that again today, talking more specifically about inverse functions. So we already saw this again yesterday, this part right here. So when you take the composite of f of g, the end result is x, and then going the opposite way, g of f, the composite of that would be x as well. You would find every x in the domain of g, and then over here, every x in the domain of f. So they're kind of like flip-flopped, and hopefully you've seen this before. The domain of f, okay, is the range of f of the inverse, okay, and vice versa. If we look at a t-chart, if we had something, let's say like 0, 1, 2, 3, and then this was 3, 6, 9, and 12, the inverse of this function would be 3, 0, 6, 1, 9, 2. So basically the y's become the x and the x become the y's and vice versa. So the domain and the range, they really switch. That's what that first part is really saying. Now, if we are going to find an inverse, we can do this pretty simply by switching the x and the y's. So, like we've said in the past, fancy way of putting f of x is as y. So y equals x minus 6. And you're going to switch the y and the x, and then solve for y. And then replace it back with the function. So the inverse of function f would be x plus 6 in this case. And if you remember, if you graph this over on the Cartesian plane, it would have symmetry over the y equals x axis. So if we do this here, we have y equals 3x, and then x equals 3y. And again, just divide. So 1/3 x equals y. The inverse function would simply be just 1/3 x. Pause the video and go ahead and do the next two. So these are what you get. Actually, let me fix 4 real quick. So this looks better. We have y equals x squared plus 3 over 2. But you'll notice I put our domain restriction. And here's why. If we look at the graph without any restrictions, it has this part to it. Whereas the original graph is just half. And so to be inverse function, every single x, y has to be accounted for in the other graph. But these over here on the left side wouldn't be accounted for because if they were over here, it wouldn't be a function. So we restrict the domain so that we can see that it's a direct reflection and everything is accounted for each one. I'm sorry, this should have been 2x so you can kind of clearly see if we put that reflection over there. Again, reflect over equal distance from there. How we can verify that two functions are indeed inverses is we can do the composite like we showed yesterday. So if I do the composite f of g and put g into f, 2 times the quantity cube root of x plus 1 over 2 raised to the third power minus 1. Notice that this cube root and that cube will cancel out, and you have 2 times the quantity x plus 1 over 2. 2's cancel out, 1's cancel out, and we get x. Again, if that composite happens and it equals x, that means that they are inverses. Okay. Again, kind of going to what we talked about just a couple minutes ago, inverse, you swap the domain and range. So if there is a point AB in the first function, then BA will be in the second, kind of like what we talked about here. If I have 0, 3, 3, 0 will be the other one. Go ahead and go to Desmos.com, put both of these graphs in, and just see the symmetry of these two, and then see that they both click on a point, click on another point, see that the inverses do exist. We talked about to be a function, it has to pass the horizontal line test. Well, to have an inverse function, it not only has to pass the vertical line test, but it also has to pass the horizontal line test. So very similar, you would just scan the graph horizontally, or with a horizontal line going up and down. So not only does it have to meet both vertical and horizontal, that makes it what we call a one-to-one function. If it is a one-to-one function, then it means an inverse function does exist. If it fails either one of those tests, it means it is not an inverse function. That goes back to kind of this graph that we saw before. This blue line, if that would have been a full sideways parabola, it would have failed the vertical line test and wouldn't have an inverse.